In this Dynamics of Dark Energy paper, in the first lecture, we have first reviewed what we are going to get in this paper. So we have first read about the abstract part where we have got all the details, and now in this video we are going to talk about introduction. So if you want to know what is this paper all about, you have to check out my previous video. The link is you can find the link in the I button. So we will first read a simple introduction, that what is this about. We are not going to cover the whole introduction, and then we will start with the second section where the mathematics will play a role, and we will understand some elementary thing before we are going to start dark energy. Over the course of past decade, evidence for the most striking result in modern cosmology has been steadily growing, namely the existence of cosmological constant, which is driving the current acceleration of the universe as first observed in reference 1 and 2. So whenever you see REFS, it is called the reference, and whenever you see any number in a square bracket, it is called the reference 1, 2. And when you see the reference section, you will get in which reference they are talking about, or what is the reference from which this sentence has been quoted. Although it may not have come as such a surprise to a few theorists who were at that time considering the interplay between a number of different types of observations, for the majority it came as something of a bombshell. The universe is not only expanding, it is accelerating. The result first published in reference 1-2 have caused a sea changes in the way we have started thinking about the universe. Conventionally, the world of particle physics and cosmology has been seen as overlapping in the early universe, particle physics providing much needed source of energy density during that period, leading to processes like inflation, baryogenesis, phase transition, etc. Now, though we need to understand the impact particle physics has on cosmology today, how else can we explain the nature of this apparent cosmological constant? In the first lecture, I have told you about the cosmological constant lambda, which Einstein has introduced, and now this is causing the universe to be accelerating expansion. Now we want to understand what is this cosmological constant, and the way to understand is from the particle physics point of view and the cosmological point of view. Theorists never sort of ideas have come up with a number of particle physics related suggestions, as well as number completely unrelated to particle physics, to help us understand the nature of acceleration. So there is there is a key problem that we have to explain, and it is fair to say it has to be yet understood. The value of energy density stored in cosmological constant today, which rather paradoxically is called dark energy, has nothing to do with dark matter. Now this value has to be order of critical density, namely rho lambda is approximately as 10 to the minus 3 electron volt to the power 4. So this makes this rho to the power lambda to be very small. Unfortunately, no sensible explanation exists as to why a true cosmological constant should be at this scale. It should naturally be much larger. Typically, since it is conventionally associated with the energy of vacuum in quantum theory, we expect it to have a size of order of the typical scale of early universe phase transitions. Even at the QCD scale, it would imply a value of rho of lambda must be 10 to the minus 3 of GeV to the power 4. The question then remains, why lambda got the value it has today? So this arises the problem of cosmic coincidence. So if you are a cosmologist, then you have to have the greatest problem that why this value is so small, why this value, this cosmological constant adapted this very small value. So this is covering on the question of cosmic coincidence, that why dark energy dominated now but not before. So rather than dealing directly with cosmological constant, a number of alternative routes have been proposed which skirt around this theory issue. In these things you can find. They come in a number of flavors. An incomplete list includes quintessence model, which invokes an evolving canonical scalar field with a potential. So we have to understand what is the meaning of canonical scalar field and what is the potential that will play its role, effectively providing an inflaton for today, and makes use of scaling properties. So we will again see what is the scaling properties and tracker nature of such scalar fields evolving in the presence of other background matter fields. Scalar field models where the small mass of quintessence field is protected by an approximate global symmetry by making the field a pseudo number Goldstone bosons. Chameleon fields in which the scalar field coupled to baryon energy density and is homogeneous, being allowed to vary across space from solar system to cosmological scales. So chameleon field is another field. A scalar field with non-canonical kinetic term known as K-essence. So K-essence means that it has non-canonical kind of structure based on earlier work of K-inflation, modified gravity arising out of both string motivated or more generally general relativity modified actions, which both have the effect of introducing large length scale corrections and modifying the late time evolution of the universe. The feedback of non-linearities into the evolution equations, which can significantly change the background evolution and lead to acceleration at late times without introducing any new matter. It shows that if you just modify the gravity, space-time will create an effect in such a way that it will lead to an acceleration at late times. So we don't need to introduce any such different fields which actually depict the dark energy. So we have introduced quintessence and then chameleon fields, K-essence, some modified gravity fields, and so on. In the market, you can see also Chaplin gas, which attempt to unify dark energy and dark matter under one umbrella by allowing for a fluid with equation of state which evolves between the two. Tachyons arising in string theory, the same scalar field responsible for both inflation in early universe and again today known as quintessential inflation. The possibility of network of frustrated topological defects forcing the universe into period of X. The possibility of network of frustrated topological defects forcing the universe into period of accelerated expansion today. Phantom dark energy and ghost condensate de Sitter vacua with the flux compactification in string theory. The string landscape arising from multiple number of vacua that exist when the string moduli are made stable as non-abelian fluxes are turned on. The cyclic universe, causal sets in the context of quantum gravity, direct anthropic arguments, all of these are more or less exotic solutions to dark energy question. So now you can see there are a number of possible solutions you can have for the dark energy, from the modification of gravity to the phantom type dark energy or tachyon type dark energy or ghost condensation or from the string landscapes. So there are cyclic universe. There could be many possibilities, but we don't know which one is perfectly correct. Therefore we have to explore all these things. These possibilities and more have been discussed in the literature, and many of them will be discussed in detail in this review. Given the strength of the data, which are all effectively indicating the presence of cosmological constant type term today, then any dynamically evolving contribution must resemble a cosmological constant today. So the way cosmological constant has been introduced with Einstein's theory of gravity is very much convincing with data. So if you are looking for any kind of alternative, it must be in such a way that it has to depict the cosmological constant. So if you introduce any type of scalar field, it has to be depict cosmological constant, that okay, more or less it should behave like in cosmological constant. So there is a very interesting challenge that we theorists face. If you see the dynamics of the dark energy equation of a state, we have to probe back in time. A number of routes in that direction have been suggested and plans are underway to extend this even further. For example, by looking at the detailed pattern of anisotropy in the cosmic microwave background. I already told you that we can extract data from CMB. We are seeing when and under what conditions the photons left the surface of last scattering. When photons decouple from all the other matter. So the universe expanded and cooled down and the first atom formed. Therefore the photons becomes decouple and they can freely move. That is called the surface of last scattering. As they propagate towards us today, they will have traveled through gravitational potentials determined by nature of dark matter and dark energy. And so different forms of dark energy could in principle have led to different contributions to quantities such as separation of CMB peaks. So from the CMB you can have this kind of structure, like these are peaks you can see in the CMB. So as you can see that these photons from the CMB last surface, they have to travel through gravitational potentials. Therefore if you can model the different dark energy, they will correspond to different peaks which can be observed in the CMB. The integrated Shack-Wolf effect, the nature of galaxy formation, the clustering of large-scale structure as measured through quantities such as sigma 8, the propagation of light through weak and strong gravitational lenses, and simply through the evolution of Hubble expansion rate itself, which is a function of energy contributions to the Friedmann equation. Now here comes very interesting portion. On the other hand, what if the data is misleading us and we do not require any effective cosmological constant? A minority of cosmologists have argued forcefully that the majority of data as it is presently stands can be interpreted without resource to cosmological constant. Rather, we can explain it through other physical processes. For example, by relaxing the hypothesis that the fluctuation spectrum can be described by single power law. On the other hand, perhaps we do not yet fully understand how type 1a supernovae evolve, and we may have to eventually think of alternative explanations. Although this might well be the case, there is growing body of evidence for the Although this might well be the case, there is a growing body of evidence for the presence of cosmological constant which does not rely on supernovae data to support it. In the same vein, Plager recently discussed observation of cluster of galaxies Abel 194 and has argued that the distribution of galaxy redshift is fitted better with an Einstein-Strauss vacuolar region of space-time as opposed to cosmological concordance model with a lambda. Of course, this is based on limited data, but we should remember the need to always be prepared to test the standard model against observation. However, the more accepted interpretation of the data is that it is becoming clear that consistency between the anisotropies in CMB and LSS observations imply we live in a universe where the energy density is dominated by cosmological constant type contribution. An impressive aspect of this consistency check is the fact that physics associated with each epoch is completely different, and of course it occurs on different time scales. It appears that consistency is obtained for a especially flat universe with the fractional energy density in matter contribution today, omega matter approximately 30%, whereas for the cosmological constant we have 70%. In this review, we assume that the dark energy is really there in some form, either dominating energy density or through some form of modified gravity, in both cases driving our universe into second period of accelerated expansion around a redshift z is order of 1. It means that first in the inflation era universe has gone through rapid acceleration, and now our universe is again in the realm of rapid acceleration. So what caused this time acceleration we had to know. So that is the problem, that why we are observing this acceleration recently. Most of the observational results are based on the years of analyzing the first year WMAP data and has not yet reached the stage of analyzing beautiful new data published around the same time as this review was completed. Now we have multiple data like from Planck data, Bow data, and people are using this data to understand the cosmic acceleration, and they came to a conclusion that yes, there exists cosmological constant, and they test both modified gravity as well as the scalar field and different other fields which can explain the realm of cosmic acceleration. Fortunately for us, many of the key results of WMAP 1 have stood the test of time and statistics and appear to be holding true in 3-year data as well. Our goal is to introduce the reader to some of the theoretical model building that has gone into understanding the nature of dark energy. We will include string-inspired models, uninspired models, phenomenological models, modified gravity models, etc. So in this review, we are going to see all of this. We will look into the observational implications associated with dynamical dark energy and investigate the ways we may determine whether or not there may be a lambda term out there governing our universe today. Now, point of caution. What authors tells us about this review: the reader is about to spend a great deal of time learning about models of dark energy. The fact remains that although many of us believe some sort of dynamics is responsible for the dark energy, such is the sensitivity of current observations, there is no evidence of an evolving dark energy component. Everything remains perfectly consistent with the simplest model, not from the particle physics point of view, of a time-independent cosmological constant. So this cosmological constant is time-independent. Indeed, if we include the number of required extra parameters needed to allow for dynamical dark energy as a part of selection criteria and apply Bayesian information criteria to carry out cosmological model section, then there is no need at present to allow anything other than cosmological constant. Nevertheless, this may change in future as observations improve even more, and it remains important to pursue alternative models of dark energy to distinguish them from the cosmological constant observationally. So here we have the cosmological constant and different scalar field models. So as the observational data come and we will analyze, then we will see that how these other models of cosmological constant like scalar field models, how they are different from each other, although they are saying that in late time they will produce this cosmic acceleration. So before we set off, it is worth mentioning here the approach we are adopting with regard the way we are classifying models, because to some having a list of apparently unrelated possibilities may not seem the best way forward. We are treating all these possibilities separately, whereas in principle a number of them can be related to each other as variants of theories carrying the some sort of signature. See examples, some references. Our reason for doing this is that we believe the models themselves have now become accepted in their own right and have had so much work done on them that they are better being treated separately without trying in this review to discuss the conformal transformations which link them, although we take on board the fact that some of them can be treated, some of them can be related. Now, throughout the review, we adopt natural units like speed of light, Planck constant to be 1, that is called natural units, and have a matrix signature. We will use the matrix signature minus, plus, plus, plus. In particle physics, you will work with plus, minus, minus. In cosmology or general relativity, we work with rather minus, plus, plus. We denote the Planck mass MPL is equal to g to the power minus half is inversely proportional to g, which is Newton's gravitational constant, is came out to be 1.22 into 10 to the power 19 GeV in the energy scale, and the reduced Planck mass as MPL is equal to 8 pi g to the power minus of half, which is equal to 2.44 into 10 to the power 18 GeV. Here g is Newton's gravitational constant, where kappa square is defined to be 8 pi g, where kappa can be called as the Max Planck mass. 8 pi MPL to the power minus 2, it is denoted as MPL, capital MPL minus 2, and we will use unit kappa square to be 1. So we will use also Planck mass to be 1 in some sections. Finally, we would like to provide guideline for approaching this review. Some of section and subsection are specific interest and may be skipped over in first reading. So now we are going to start with elements of FRW cosmology. What are the elements we have to understand in order to begin with FRW cosmology?